One of you emailed me with a question which I didn't answer. No one fesses up. Apologize for not having answered yet. Definitely, if you're having trouble with the homework, right, you want to go to the discussion section tomorrow, right, the recitation. Though I'm not necessarily, you guys occasionally can ask me questions about homework, but in general, I'm not going to have time to answer it in session here. As it says on the syllabus, though, if you want to meet with me, just schedule a time, send me an email, okay? Or you can pop by my lab, which is 118 Rockefeller. I might not always have time, but if I do, I'll certainly meet with you, okay? That's where I mostly live. I'm sometimes in my office, which is right down there. And that's also on the syllabus. Okay. So today we're going to continue looking at a couple basic things. Oops. How does that work? There we go. A couple of basic things in special relativity. In particular, we're going to look at two famous paradoxes. So kind of show the paradox, and then I'll show sort of the analysis, which may not make everything completely clear, but should make things a lot clearer, I hope. And at least the real point of going through these paradoxes and the analysis is to show you how to think about these problems, okay? Which will translate to your homework and just in general. Okay. One famous paradox is to consider Anna in a spaceship. And Anna has a spaceship of length L0. So I'll write A for Anna's frame. And Bob has a spaceport. And the question is, does the spaceship fit in the spaceport? So Bob has a building of distance d, of length d. And the point is, what if d is less than L0? Simple enough, okay? However, if Anna is going fast enough, and in particular, if Anna is going a speed, hello? So if Anna is going a speed such that gamma is equal to L0 over d, all right, Bob sees length 1 over gamma L0, right? And so Anna just fits. So very simple idea. The space station is too small for the ship, but if Anna's going fast enough, it goes racing in a door. Suppose there's two doors. Three-dimensional thing. And there's a door here and a door there, and Anna's ship goes right in. Okay, there's an instant in time, Bob says, when Anna's ship actually fits. Okay, that's strange enough because there was length contraction. By the way, sometimes the length contraction is called Lorentz contraction from the Lorentz equations. What's the paradox? Well, there's kind of two paradoxes. One version of the paradox is, of course, what does Anna see? And as I've pointed this out before, Anna also sees Bob's station contracting. In fact, what does Anna see? Anna sees a contraction. She sees the station having a length of 1 over gamma times d. And by the way, we set up the problem. We said she's going at exactly the speed that gives gamma so that d was equal to 1 over gamma L0. That's the same as this statement here, all right? So in fact, Anna sees 1 over gamma squared L0. So Bob saw Anna's ship contracting down and fitting just in. Anna sees Bob's station, which was already too small, get a factor of 1 over gamma smaller. So this is utterly too small. This is much less than L0. So Bob says Anna fits. Anna says the ship doesn't fit. And that's the basic paradox. Sometimes you'll see a discussion about, well, what if Bob closes both doors right at that instant when Anna is inside, right? Then what happens, right? If the spaceship stops, suddenly it's bigger. You know, how does that work? Well, the fact is, if she closes both doors, you know, there's going to be this terrible collision. The ship's going to get crunched down. That's part of this resolution to that. But really, let's just use, well, what do you think is the basic, what is the basic resolution? In fact, if you saw what we did last week and you've worked on the homework, you should know the answer, right? But what's the basic resolution? Yeah. Okay, the time is the issue. Certainly in Bob's frame, he can close both doors at one time. Okay? But if Bob has one time in his frame, are you looking at one time in Anna's frame? No. The resolution for the door part is indeed that, yes, there's an instant in time in Bob's frame where the spaceship is fully in, but Anna's in a moving frame, and it's a little bit of a cop-out, but the frame would have to stop to have Anna actually stuck inside, and that you get into acceleration and general relativity. So we'll come back to that, okay? But the fact is that that's what's going on. We're not looking at one time in Anna's frame. So let's just go through this in detail. Let's look from Bob's point of view. From Bob's frame. So let me just lay this out carefully. Let's consider, we consider the instant when, in Bob's frame when the spaceship is just in. And let's just draw and label the two frames. So here's Bob's frame. It's the X frame and the T frame. Let's say X equals 0 is the front of the barn. This is often, when I first read this, it was barns and ladders. Some guy running really, really fast, okay? Or you do trains and train stations. Because, of course, Einstein's papers, he talked a lot about trains and train stations. But now we do spaceships and... Anyway, so this is when the front of the space station with the spaceship just in it. So let me just sketch that. So X equals 0. I'll just choose this to be T equals 0 for simplicity. And what's the back of the spaceship? I mean, the back position? It's simply D, okay, but we constructed things. We said, well, it'll fit if that's equal to 1 over gamma L0, because that's the contracted length. And what's the time? Well, we're in Bob's frame, so the time is the same everywhere. Okay? Now let's fill out in Anna's frame. The front, let's just call it X prime equals 0. This is the prime frame, the S prime frame. Okay? I can go ahead and just say this is the same, this is time equals 0, the front, time T prime equals 0. But now to talk about what happens back here, I can get really confused and think real hard, or I can just resort to the math. All right? X prime, I'm just going to write them down. And you should be able, basically you should memorize these. All right? X prime is gamma X minus Vt. T prime is gamma minus V over C squared X plus T. Okay? So the back here, X prime, well, I lied a little bit. I can either think hard or use the math here. The back of Anna's, in Anna's frame, I mean, we agree that this is the situation. This is lining up, this is lining up, this is lining up. This is simply the back of Anna's rocket. So it must be X prime equals minus L0. However, that fits exactly with this equation. X prime is gamma times X, and X was 1 over lambda L0, 1 over gamma L0, and so gamma and gamma cancel, and T is 0. So it's the same, all right? But on the other hand, we just said, look, we're at the back of the rocket in Anna's frame, and the rocket in Anna's frame was L0 long. However, and here's the kicker, this was the one part, it's a little more, T prime equals what? Let me write it out here. T prime is going to be gamma minus V over C squared times X. Well, X is 0. No, it's not. X is not 0. X is minus 1 over gamma L0 plus T. T is 0. So then that's gamma. The gammas cancel. It's simply V over C squared L0. This is what we were talking about last time. V over C squared L0. You're looking into the future. Bob sees the back of Anna's ship fitting, but he's looking into Anna's future. And be careful with the looking into. I mean, the fact of the matter is that at this point in space, where Bob's ship is in Bob's frame, the back of the ship is at the back of Bob's barn. That is a real moment. That is an instant in time. That's a simultaneous event. The ship, the back of the ship, the back of the barn, same place. Everyone agrees on that. If Anna's at the back of the ship, she says it happened. If Bob is here, or if he's here and he has a friend reporting to him, they agree that it happened. It's just simply that. Whereas in Bob's point of view, that happened at the same time that the front was in. That's not the point of view from Anna. In Anna's frame, if the front of the ship was in at T prime equals 0, the back of the ship was in later. Anna simply says when the front of the ship was in at T prime equals 0, since this is T prime later, when T prime is equal to 0, clearly earlier the back of the ship was further out. It simply wasn't in there yet. They don't agree that there was a point in time that Anna's ship fit in Bob's spaceport. Okay? They just don't agree on that. This completes the analysis from Bob's frame. I mean, essentially, all we can work out are what are those conditions. That's the full analysis. Now I can ask a more tricky question by maybe having told you something else and told you find gamma, because I told you some other condition or whatever it is. But the fact is, this is fully thinking through the problem from Bob's point of view. Just, it was easy to write down these. I picked that as a condition, and then I have to think and use the Lorentz formula to figure out what was going on at the back of Anna's ship. Okay? So I hope that's clear. That's what we're doing. That's sort of the game here. I was picking places, setting up my conditions, and then analyzing some other place. Okay, now let's go a little further. I'll do it here. Let's look at Anna's point of view. Anna's frame. Okay? Well, let's choose the moment I've already said that in Anna's frame, she just doesn't agree that the back of the ship was lined up with the back of the spaceship, the back of the ship was lined up with the back of the port at the same time that the fronts were lined up. So we have to just choose. We can either choose the moment when these are lined up or the moment where those are lined up. And we can do an analysis either way. Let's pick when the backs are lined up. So the moment when back of ship plus port are aligned. Okay? And so let me the straightforward thing, again, is just to proceed somewhat mathematically. I'm going to take this as my initial condition at the back of the ship. X prime was minus L0 because the front of the ship is at X prime equals 0, and the ship is, its length L0 in Anna's frame. T prime here was V over C squared L0. But now we're talking about Anna's frame. Okay, so the front of the ship at this moment in time in Anna's frame is no longer t prime equals 0, it's t prime equals v over c squared L0, the same moment in time. So we're asking, what does Anna see in her frame when the back line's up? She says, well, the front now is no longer at t prime equals 0, it's later. What does she see for Bob? Well, we're still talking about that actual moment in time. That was an event. That event happened for Bob in his frame at x equals minus 1 over gamma L0. Yeah?
In this diagram, where is the front of the station?
We're about to discover that. I'm about to write that in. The front of the station for, well, okay, let me write the time down. That's a good question. Where's the front of the station? But I'm just copying. The back was at minus 1 over gamma L0, this contracted length. The time is 0. This was an event. There was that analysis, and we said the time is 0. There's a point which I don't much care about at the moment. I'll come back to, which is where's the front of it. The front of the barn is at x equals 0 at some time. Okay? And then the very front of everything, and in fact that's probably somewhere about there. And the very front of the spaceship is lined up at some time x, at some place x. Okay, let's call it that, which I want to find. Let me make a comment about time though. I had these equations. Whenever I have those equations, I have the complementary equations to go the other way. I can write it here. How do I get the complementary equations? This is, if I know that Bob's frame, the S frame, this is the prime frame, how do I get the others? We talked about this Friday. It's just the point of view. In one case, the one frame is moving in the positive direction. The other point of view, the other frame is moving in the negative direction. So it's just to replace v by minus v and switch prime and unprimed. Right? And I actually worked that out. That's also, if you simply work it out, it will work out. In fact, we used that fact to finally normalize the equations and get rid of the last unknown. Yeah?
In this diagram, the unprimed frame is Anna's frame.
No. Maybe it will help if I did it this way. Bob's point of view and Anna's point of view, okay? I still simply have that Anna's by def is always going to be in this S prime frame. It's simply that I drew the frames. Anna's moving respect to velocity v, and so her frame moves past this frame with velocity v, okay? And then I applied these equations. In that situation, if I consider this fixed, this frame is moving in the negative x direction, and so I get the minus v. But I'm simply doing this analysis. I mean, that's a sort of question that can get tricky. Let me see how to say that. How to realize that I'm not doing that. When I chose Anna's point of view versus Bob's point of view, what was I doing? I said it a couple of times, but I'm sure it may well have gone past you. What did I do that enforced that it was Anna's point of view or Bob's point of view? There was one key thing I did.
Times constant in that for that frame.
That's right. I picked a frame and I said at that frame, let's just consider everything to be at the same time. All right? I mean, I can map out the times and the distances for both frames all different ways I want. But if I want to say, how does someone experience it? In a frame that you're at rest with, you experience it as that the time is constant everywhere. Okay? So having written this down, x is just simply gamma x prime plus dt prime, and t is simply gamma v over c squared x prime plus t prime. I'm not going to write math down, but if this is t equals 0, and then I move over to the right, I'm just going to increase x prime. I started with x prime being some number. Now it was negative, but in fact, if you plug that x and that t, that x prime and that t prime into this equation, you'll find that t equals 0, right? Because x prime is L0 with a negative sign, and t prime is v over c squared L0. And there was a v over c squared there. Okay, so this is all works out by construction. It's because I used these equations to find this out. Okay, so t is 0, and then if I walk over to the right, I'm walking in towards larger x prime. T prime was all 0, but nonetheless x prime is increasing. So these are later times, t greater than 0, just increasing as I walk along here. So from Anna's point of view, she doesn't look at one time in Bob's frame. She looks at different places in Bob's frame at different later and later times moving over to the right. And very simply, x is just use this formula. It's at the front of the rocket, out here, it's gamma x prime at the front of the rocket is 0, plus v, and t prime was just this thing, v over c squared L0. Okay, so that's gamma v squared over c squared L0. So that's the distance, and what is that? That's the location where the front of the rocket sits in Bob's frame. X equals 0 in Bob's frame is where the front of his barn sits. And so this is saying that's how far out beyond the edge of the barn Anna thinks she's sticking. So when she goes racing by, not barn, spaceport, when she goes racing by Bob's already small and now Lorentz contracted spaceport, this is how far out she thinks the front of her rocket ship is sticking. Okay? And at one level, that's the full analysis. Okay? Let me just, I'm going to do one more thing with this, but I'm going to make one aside. Just a bit of notation. V over C appears all the time. And so we assign a Greek symbol to it, beta. Beta equals V over C. And in that notation, gamma is the square root of 1 over 1 minus V over C squared. Gamma is 1 over 1 minus beta squared. The book kind of uses this a little bit, but not all the time. I'm going to use it all the time, because if you're doing these equations, you get sick of writing V over C. And they do use gamma, because you certainly get sick of writing 1 over 1 minus square root of V squared over C squared. I said that wrong, but you know what I mean. All right. Let me try to do this, though. I think you should just get used to, and then it's at one level, that completes the analysis. Well, I didn't write down the times, but I could go find them. And that, in some sense, rigorously just completes the analysis. I can solve homework problems, I can solve exam problems. More importantly, I can understand the physics with the Lorentz transformations, kind of following this logic. But let's look at it a little bit, just trying to use the Lorentz contraction rules, the fact that things shrink when viewed from the other frame. Just explore this a little bit more. From Anna's point of view, again, let me just redraw in Bob's frame. We had x equals 0 here. We had the front out here at x, and we had the back, which was just the distance of the spaceport, which was 1 over gamma L0. Right? That's how we set things up. And it's minus that. So we can say overall, and this, Anna says, hey, my rocket lines up perfectly. Okay? I mean, no, that is the distance on the ground and on Bob's frame that my rocket covers. Let's call that delta x. Okay? Clearly, delta x is just simply this distance as a positive distance, 1 over gamma L0, plus that distance. That's the x, the location of the front, relative to 0 in Bob's frame. Very simple thing I wrote down. What does Anna say about that delta x? Anna says that delta x does not line up with L0. Just like if you guys go flying by, I see you shortened. She says that delta x lines up with the contracted length, 1 over gamma L0. Sorry, darn it, I said that backwards. I got to be careful. Anna says, all right, sorry. Anna says there's really a length delta x, but it looks contracted. Okay? So that right. Delta x looks contracted. Maybe this is what I wrote down. So that delta x over lambda equals 0. It's a basic idea. So, well, I think I've said it, right? That's not to say that Anna knows that in Bob's frame it's measured as delta x, and she agrees that these line up. But she simply has the whole notion, the original notion we had of just simple length contraction. She sees Bob shooting by, and so he's smaller. So she says whatever intrinsic length he's got, I'll divide it by gamma, and that's got to line up with my L0. Okay? Let's use these two equations and see if we agree on this value of x we calculated here for where the front of the rocket is. So this says delta x is gamma L0. Okay, and that's equal to this. So I have gamma L0 equals 1 over gamma L0 plus x. So very simply, x is gamma L0 minus 1 over gamma L0, or gamma minus 1 over gamma L0. Yuck. I have two expressions for x arrived at just very systematically with the Lorentz contraction, and then by thinking a little bit harder, just using the rules of, from the Lorentz transformations, and by thinking a little bit harder, just using the rules of contraction, length contraction. Yeah?
What does x signify?
I really do mean just there's a coordinate axis x, there's some unknown location on it, the point x, the distance out in front of x equals 0. Maybe I should have called it x1 everywhere. But where in Bob's frame you line up with Anna's frame, the front of Anna's ship. At that instant in time, frozen in Anna's frame, time equals vc squared over L0, where Anna's all at one time and sees the back of her ship lined up with the back of the barn. Does that answer the question?
Then does x equal 0 have any significance?
I'm saying all I'm saying is this is the x-axis. There's the point x equals 0. There's the point x equals minus 1 over lambda L0 back here. And there's some point here in the future, or over to the right, I'm just going to call it an unknown x value. Could have called it maybe x1. This is really maybe x back equals this, x middle equals 0, and x front equals unknown x so far. And I solve for it. Okay. Huh? Yeah, okay, let me do that. That's a better notation. Etc. If you want, right? This is actually a convention that people will use to say this is the x-axis, and there's some unknown value of x I'm trying to solve for. While I know some other places, and I just kind of write the number down, because that saves me from always writing subscripts. But that's only if you're used to it, and I implied that, and so I'm sorry if I went too fast. I was not trying to be confusing with that little point. Okay, is that clear now? Yeah, okay.
Versus Anna says
Uh-huh.
Isn't delta x smaller than L naught in the frame?
Well, you see that I got confused, so I don't blame you for being confused. Let's think that through again. Anna's rushing by. She says, my length is L0. She says, I'm at rest. Bob's ship is going by. Whatever Bob's real length is, I see it shortened. So 1 over gamma times Bob's real length lines up with me. Okay? This is the straightforward way. This is a subtle way. Okay? If you have to remember anything, pretend this nightmare didn't happen and just remember this. Okay? But now let me show you something neat. You are going to run into cases where you have some expression in your homework and whatnot, where you have some gammas and you have some gammas and betas. So in fact, I didn't finish writing this down. The way we like to write this is gamma beta squared L0. Is gamma beta squared equal to gamma minus 1 over gamma? That's the question. If that's the case, then those two are the same. And in fact, it is. And let me just show you. There's one little trick. If you ever have beta, well, sometimes gamma is inconvenient and sometimes this beta is inconvenient. It turns out like one of the most common things you would want to do if you've taken, you've done mechanics and you're used to normal life, you'll always be asking in special relativity, well, what's the velocity? And quite often what you get out of a problem is you learn what gamma is. And so the velocity is like buried under this horrible, square root and all this stuff. And so you have to do all this algebra to find out what the velocity is. And sometimes then you have problems where the answer is a mixture of gamma and beta. I mean, it's a simple problem, but imagine solving this for velocity. You're just going to have to write everything out in terms of velocity and then start doing some algebra. And it's like messy, messy, messy. One answer is actually we don't ask what the velocity is in special relativities. We really typically only care about gamma. Because beta, if anything is going fast, is a number really, really close to 1. Okay? I mentioned that last time. But in any case, if I do have gamma and beta and I want to get rid of one or the other, there's a simple trick. What's gamma squared? It's 1 over 1 minus beta squared. Okay? So let me multiply both sides by 1 minus beta squared. So gamma squared times 1 minus beta squared is 1. Right? So then gamma squared minus gamma squared beta squared plus gamma squared equals 1. That is to say, gamma squared beta squared is gamma minus 1. That gets rid of beta in terms of gamma alone. The gamma squared minus 1. Okay? Therefore, in this problem, we had gamma beta squared. Well, that's just this divided by gamma. So it's gamma squared minus 1 over gamma, which is gamma minus 1 over gamma. Lo and behold, gamma beta squared is gamma minus 1 over gamma. So this is equal to that. So those analyses are the same. If you don't remember exactly how to derive that so simply in one line, you can get really lost. You might want to just practice that little thing. You just write down what gamma is, square it, and then eliminate beta. And then it's just really simple to get that relationship. What you do not want to do, if you have something like gamma minus 1 over gamma, you do not want to plug in 1 over the square root of stuff minus 1 over the square root of stuff. Do not do that. Don't. Okay? You'll just get nightmare. Okay, so that's sort of the the full treatment of the famous spaceship fitting in the spaceport paradox. I think we've kind of beat it to death. So now let's do another paradox. This is the so-called twin paradox. Since we started off with Anna and Beta, Anna and Bob, these are going to be fraternal twins. And the basic setup is that they're born the same day. They're twins. And immediately they're separated. So they're twins separated at birth. And Anna, for some reason, and it's something out of a Star Wars or something, so she's taken away in a spaceship. Actually, it is the Star Wars setup. I hadn't thought of that. Huge geek quotient here. They're right. So the moment they're born, Anna is stuck on a spaceship, heading it, and I'm going to pick some really convenient numbers. The velocity is 0.8 c, okay? Which is to say beta is just 0.8. And she's taken away to some star that is 40 light years away. Anyone not know what a light year is? Okay, it's the distance light goes in a year. So what's convenient about that, if I have the distance light goes in a year, and I say, how long did it go? If I divide by the velocity in c, then I just get the years. Okay? So Anna is taken out, and then when she gets to the star, so this is initial, and then when she gets to the star, her spaceship is instantaneously reversed, and she comes back to Bob. Okay? So, I'm not going to follow the niceties of trying to exactly, my notation, question or?
Yeah, don't get into this, it's complicated, but is the reason why you specify instantaneously is acceleration has some sort of effect on it.
Yes, but that is complicated, and I will get to that, but the reason I did it was simply that I don't want to talk about how long she spent accelerating and decelerating. I just want to talk about she went out, and she came back, okay? And we'll just pretend, someone just changed the movie right then, bink, in one frame, and she's coming back, okay? That's the only reason I actually did it, okay? And I'm not going to pay attention for this argument to the niceties of writing down the Lorentz transformations. I'm going to work more like I did, which in general I don't want you to do because it's more confusing, requires more thought, I think, but is important to go through this thought than simply writing down the Lorentz transformations, okay? So, but I have to be careful about the way I say things. So what does Bob see? Or here's what Bob says. I will just use the notation a little bit different than I just did. Well, no, sorry. Let me not try to confuse things with that notation. Let me just do it this way. Okay. So what does Bob say? Bob says Anna went out. So Bob says t half for Anna. The time it takes to go out, and then that's half the time because clearly it's symmetric. She goes out for some time, she comes back for some time. Very simple. She went 40 light years at 0.8 c, which is also, and so the c will cancel out, and so it becomes 40 years. And 8/10 is also known as 4/5. So that's 10. That's 10 over 1 over 5. That's 50 years. So, or sorry, that's t1 half. Sorry, I'm sorry. That is how much time Bob sat and watched this happen. So t for Bob is 100 years. Okay? Now, Bob says this is also how long he watched Anna go, but Anna was going at 0.8 c. So Bob says that t1 half for Anna was this 50 years over gamma. Fair enough? Now 0.8 c and 0.6 c are magic values for gamma based on a 3, 4, 5 triangle. Gamma is 1 over 1 minus beta squared. Beta is 0.8, but that's also known as 4/5. So this is 1 over the square root of 1 minus 4 squared over 5 squared, which of course is 1 over the square root of 5 squared minus 4 squared over 5 squared. Right, so that's 25 minus 16 is 9, which is 3 squared. So all of this is 5/3. Right? Okay. That's why I picked it. All right. So this is 50 years over gamma is to multiply it by 3 over 5. So that's 30 years. 5 cancels the 50 and you get 10. So T Anna is 60 years old. So that's the basic, thing I think I mentioned last time, right? So there's this whole, and it's a famous idea from relativity, right? If someone goes whizzing out and comes back, you've aged more than they have. And of course, if we'd pushed gamma to be 1,000, then Anna would have aged, 5 months. Bob would be 100 years old, right? But okay, so there we are. What does Anna say? I mean, we know this is going to be weird, right? Because Anna thinks Bob was moving, while Bob thought Anna was moving. So shouldn't Anna say that Bob is younger than her? Indeed, yes. And let's just see how it works out. Okay? It's not quite as simple. I mean, it's a little bit more than you might think. Okay, so here's what Anna says. So first off, she raced over from the home planet from Earth, or Tatooine or whatever, to the star, and 40 light years. But she's going at 0.8c, so she sees L, which is 40 light years, but contracted by gamma, right? She sees it contracted. Again, I could use the Lorentz transformations to sort of write all this down, but I'd be using very simple versions of it where the time is all the same for Anna's frame. I'd be using simple versions of it, so I'm just going to write that down. And so gamma is 5/3, so this is 3/5 times 40, so that's 24 light years. Okay? So the time that Anna thinks she aged, the half time, I wrote it the other way, half time for Anna is simply, is the distance is 24 light years divided by 0.8c, which again, it's 24 over, that's 4/5, so it's 24 times 5/4, so that's that's 30 years. Okay? So Anna believes that the full time going there and back is 60 years. The back is the same analysis, right? It's just completely symmetric. She's now going the other direction, same contracted distance, same velocity, same answer. Double it, 60 years. That's also what Bob said was the case for Anna. So far, so good. But what does Bob say, what does Anna say was the situation for Bob? T1/2 for Bob is discussed by Anna. So Anna's coming over. It's simple. She saw 30 years pass for herself. And she says Bob slowed down. Okay? So that was 30 over 5/3, which is to multiply 30 by 3 over 5. That's 6 times 3 is 18. So Bob aged 18 years on a pop, 2 trips. So she says Bob is 36. So that is quite a paradox. Anna comes out, leaves, comes back, they meet again. Bob is 100 and at the same time 36. All right? So now within the framework of special relativity, that should not happen. We can get paradoxes or weirdness in the sense that I see you moving past and I think, and I'm seeing in your future over there and your past over there a little bit. but always events should line up. Remember the idea of the light bulb. You know, we should agree on, on a simultaneous event. And here we're talking about Bob and Anna being born together, and then, dying together at, Bob's age 100. And they don't agree, okay? And so this is actually just simple, and this is the twin paradox, but this is simply a failure of special relativity. Why? Because someone asked. It's because there in fact was enormous acceleration at the time when she turned around. And special relativity, like when Newtonian F equals ma, if you don't talk about so-called fictitious forces and not in accelerating frames, so in the same way that Newtonian mechanics applies in inertial frames in the simple way, special relativity only works in inertial frames, i.e. no acceleration. And I know this sounds like a cop-out, but it is the real answer. If you wanted to treat this problem correctly and include the massive deceleration and re-acceleration that Anna experienced, that requires general relativity, okay? And so one way of saying general relativity is to say that, well, general relativity is, when frames, hold on. General relativity applies when frames accelerate and decelerate. More generally, though, general relativity had to do with gravity. What does gravity have to do with this? This is neat and deep. Who's to say Anna wasn't in an inertial frame and Bob accelerated out over that way, suddenly stopped and accelerated back the other way? Anna could say that happened. There's this notion, which I don't know if you've heard, predates special relativity. I think it's that I forgot the name isn't coming to me. German name, thought about the notion of what really sets an inertial frame, and that the idea is that it's the entire universe that's setting the inertial frame. Okay? And so in fact, it's sort of the presence of all the matter in the universe which picks what is the inertial frame. And that is understood in the framework of general relativity. And that's why it's general relativity that it says it. So in order to for Anna's frame, where Anna says, I was at rest and Bob did this whacked out thing, you actually have to include enough physics to talk about Bob and all stars and everything and the basic. There is sort of, in some sense, a rest frame for the universe. There's an overall expansion due to the Big Bang, but there's sort of, nonetheless, you kind of factor that out. There's a rest frame, if you will. And you're saying, oh, but in here, the whole frame went, suddenly stopped, and then reversed and came back. And that would clearly be treated within the framework of general relativity, okay? So Anna did the special thing. She accelerated and decelerated. So she's basically wrong. She's just wrong. She's wrong about Bob, okay? That's all there is to it. Well, she wouldn't do this analysis because she's really smart and she studied general relativity, and she says, I didn't include general relation of relativistic effects, okay? No. Okay, so we'll talk about this some more. We'll stop here.